All right, well, let's get started because I know we've got a lot to get through. So hello, welcome everyone, welcome back. Sorry about the little bit of a long time between meetings, but we're super excited to be back and starting these meetings again on formal demography related topics. Just because it's been a while, I thought I'd just reintroduce everyone. So this group is organised by myself. I'm an assistant professor in statistics and sociology at the University of Toronto. Vanessa DeLago, who's a research scientist at the Vienna Institute of Demography, and Rio Moji, who is a postdoc at CPOP in Denmark. I think, and you've only been there, or maybe it's a long time now, about 6 months. It's quite a new position. So before we get started with today's talk, I just wanted to make 2 announcements. So the first one, I think many of you probably know, but the journal Demographic Research is organising a special collections in memory of Jim Vopel. And so if you work on topics that are sort of related to Jim's work, so formal demography, longevity, ageing, biodemography, that sort of thing, please consider submitting to the special collections. The details, I'll just put the link in the chat. Submissions close on the 15th of October. So you have to sort of give present your idea, and then there's a series of guest editors who will sort of evaluate and then choose a selection of people to contribute. So please consider that if it's relevant to you. And then the other thing I wanted to mention was we haven't met for a while, but we've got 2 meetings in very quick succession. So the next one's in a couple of weeks. We're going to have Ariel Kalinski talk about the World Mortality Data Set, which has been formulated quite recently, and it's been really integral in excess death calculations for, since the pandemic. So excited for that. Details are on our website. And now, Rio, if I'll hand over you to introduce our speaker.
Yep. So nice to see you again, everybody. So today, my colleague Marie-Pier, same institute, is going to introduce or is going to present her 2 works about lifespan inequalities, and she tailored. So she is an assistant professor at CPOP first, and then I should say that. And then, so she tailored her slides for formal demography group with full of equations. So get excited. So please, Marie-Pier, it's your floor. Thank you.
Yeah, thank you for the introduction, Rio and Monica. So I'm going to share the screen to start with. Okay, can everybody see it? Can you see the presentation or no? Yes, okay, good. Just gonna, okay. So, well, first of all, thank you very much for inviting me to give this talk. I think the idea of this group was very fun, to have this network of people interested in formal demography. So really thank you, Monica, Vanessa, and Rio for organizing this. So today I'm presenting a combination of 2 papers, if we want. So about this outsurvival statistics. So the first paper was leading by Jim Vopel, and it's mostly the formal demography of the statistics. And then the second paper is the application. I think in this the BMG Open article that you might have seen together with the announcement of this talk, which is an application of the statistics to study sex difference in lifespan. So this both work have been done in collaboration with Jim Vopel, with also Elia, that I see was online, and also Rizus Adrian Alvarez and Virginia Zaruli. So a bit of background on why did we started studying this. So in 2019, basically, Jim Vopel came to me and asked, what do you think is the probability that male outlive a female? So he was especially curious of that question because he had a lot of grandsons, and he wanted to know, are they really that disadvantaged in terms of lifespan by simply being male? So that was a good question. Never really thought of it. And then he added that his gut feeling said that this probability of male outliving female was 40%. I never really worked with gut feelings in the past, and I thought maybe that was a little high as a probability, but decided to look into this. So first part, so how can we assess this probability? Well, the probability to outlive someone that we call here outsurvival relates to this overlap between two lifespan distribution. So if we have, for example, all male dying at age 80 and all female dying at age 85 with no variation around the means, then the probability of male to outlive female would be 0, because all male die at 80 and all female die at 85. But because we have this variation around the mean, so there's a lot of lifespan variation, we tend to have this overlap between two lifespan distribution. So we have some male, for example, that die at 90 that live longer than some female that, for example, die at 70. So this measure of overlap, or this study of overlap between two lifespan distribution, have been studied in demography in the past. So there's two key articles, one by Edward and Tujapurkar in 2005, where they look at the Kullback-Leibler divergence. So this the KL divergence is basically interpreted as in the context of sex difference into how much effort would it need to transform the male distribution into the female distribution, female lifespan distribution. And then there's a study by Shi et al. In 2002 that measure basically what's the area of overlap, of non-overlap between two lifespan distribution. So how much are they overlapping? And this was used as a stratification index, especially to study difference in lifespan between socioeconomic group. But none of these indicators basically give us a probability. They give us an indication of how similar or dissimilar are the two lifespan distribution. So we decided to then investigate how we can obtain this probability. It was during COVID time, or just a bit before, so both Jim and I kind of work on it on our own, and we kind of derive the same probability, but via two different angles. So if we're interested in estimating the probability that a random individual from a population A outlive a random individual from a second population that we name B, so we can have a life table perspective. So we call this outsurvival statistic phi. So if an individual of population A is still alive at age X, then that individual outlive somebody that died at age X in the population B. So outsurvival statistic can be calculated by multiplying the survival function in population A by the age at that distribution in population B, both found in the life table. But we can also have a more generalized perspective into this. So if you look at any density probability function, so it can be not just age at that distribution, but any kind of distribution, income distribution if you want. So the probability that an event happened in population A, so at age X, or it can be a time or anything, well, that event will happen before all similar event happening before age X or time T in population B. So F here, the small f here is the density probability function, and the capital F, it's the cumulative density distribution. So those two equations can be equivalent if we reformulate it in the context of life table. So if my density distribution is my age at that distribution here, and my cumulative density distribution is the cumulative age at that distribution, here called capital D. So it can be shown that both formula are equivalent. So in the first option, we have if individual in population A are still alive at age X, then they outlive somebody that died at age X in population B. And via the other one, so if an individual in population A die at age X, then they still live longer than everybody in population B that died before age X. So these two approaches can be equivalent. So the first one is So if we go back here, so the first approach is mostly developed in the sense of this out-survival statistics and how it can be applied in the life table. But the second version can be applied to various different contexts. So what would be the probability that a female have a higher income than male, for example, in a given year? So it's a bit more generalized. But if we look mainly at the first option for the life table, so there's a complement to this out-survival function. So what's the probability of a random individual in population A to outlive someone in population B, then it's 1 minus the probability that someone in population B outlive a random individual in population A. So the sum of those two functions equal 1. Basically, they're complementary to each other. And we can again rewrite this formula here. So the age-added distribution is a function of the force of mortality in population B multiplied by the survival function in population B. So it's simply rewriting the formula like this. Then I do that because we can derive some related result or mathematical related result based on this function. So just a few extra results. So if we assume that population A and B have the same force of mortality, then they have the same age-added distribution and the same survival function. And then using this notation, we also can see that if this hypothesis is right, then the force of mortality multiplied by the square and survival function would give you the out-survival statistics. And in all cases, this is 0.5. So if two populations has the same force of mortality, then the probability that someone from one population outlives somebody from the other one is 50%. So it's a 50-50 kind of risk. So if equal mortality, then the out-survival statistic is 50%. Then if we play a bit more around with those equations, so let's assume that the force of mortality of population A is constant over age. Just assume it's mu for all age. Then the force of mortality in population B is half of that. It's constant over age, but it's half that of population A. Then we can see that life expectancy in population A is 1 divided by mu. And the life expectancy of the second population, it's twice that value. So if we then input those values into out-survival statistics, so that will equal to the force of mortality of population B time, this is the survival function of population B expressed as a function of mu, so the force of mortality, and then the same thing for population A. So the integral of this function is the force of mortality of B divided by the force of mortality in population A plus force of mortality in population B, and this is 1/3. So even in a case there mortality is half, population B is half of that, and population A in life expectancy in double. So if we assume, of course, constant force of mortality over age, there's still a 1 in 3 chance that individual in the first population outlive someone in the second population. So there's still a fair amount of overlap even in this context. So these were mostly like formal relationship or where we're coming from with the statistics. So it's always fun a bit playing around with the math and getting some what we think were new formulas, but then we start looking into the literature and we see that that has been done many times in other fields. So the out-survival statistics relate to plenty of other statistics. So we have this expected failure probability and the stress strength interference model. So basically, what's the probability that the stress put in the material excess its strength? There's also this probability of superiority. So what's the probability that a random score in one sample is higher than a random score in a second sample? And then there's also this Mann-Whitney U-test. And after we published this article in Demographic Research, we also had a letter response saying that the statistics also relate to the ROC curve. So it's been done plenty of other time in plenty of different ways. So it's nothing, the math is not necessarily new. but the application in demography was somewhat new, at least, that we think. One more formulas. So far, we've been showing everything in terms of continuous relationship, but as you all know, we mostly work with discrete data. So we derive a formula to estimate phi for discrete data. So it's simply the sum of the product of the survival function and population A multiplied by the age-added distribution in population B at age x minus n. So n being the width of the age group. So, and then we have one more element in this equation, which is this d bar, which is basically it's the probability that individual in population A and B died in the same age group. So if we have a 1 year age group, so what's the probability that male and female died within the same age group, which is the sum of the age-added distribution in population A and population B divided by 2. So we did a lot of simulation of continuous, we start with continuous estimation and then try to approximate which discrete model would best approximate phi. And this was the best result we have. And if you compare the discrete and the continuous approach, this is basically equivalent. There's very, very minor differences, at least for very small n. So the larger the n, the bigger the differences. Of course, if you have 10-year age group, then this contribution become bigger and bigger, and then you might have more and more disparities. But for 1 or 5 year age group, this formula is generally give a good approximation of phi. So this was the math, the first part. Then the second part is that we applied this model to understand sex differences in lifespan. Now, so we use all population we could find in the human mortality database. So that's a total of 44 population since 1751. So that was the year for Sweden, and then slowly we have more and more data over the years, or more and more population over the years. We also use the data from the World Population Prospect in 2019. So this is average life table, of course, by sex. So we have 199 population, and this database started in 1950 by 5 year age group. So the last age group we have is 2015, 2019. And we also look at outsurvival statistics, so the probability that male outlive female across marital status and education level in the US in 2015, 2019. And for those, we use the multiple cause of the data set from the National Vital Statistics System, and also the American Community Survey to estimate the exposure. So those are first results. So the first graph is the result for the HMD countries. So, and this is the phi statistic. So here interpreted as probability of male to outlive female. So up to about the First World War, we had a phi of around 47, 48% across all HMD population we had information on. After the First World War, it started decreasing. So probably this phi statistic decreased over time. So there's less and less chance that male outlive female. And then it has restarted increasing since, depending on the population. So between the late 70s or early 2000 for Eastern European countries here. So in recent year, the phi is generally for the HMD data around 37%, and in countries like Denmark and Sweden, above 40%. So Jim's gut feeling was right again. So we can see that in the HMD data, we only have one point in time where phi has been higher than 0.5. So there was a small male advantage in that year for Iceland, but we see it never goes below 25%. So at no point in time we could find a phi statistics that was lower than 25%. So there was if for any pair of randomly paired men and women in a population, for every 4 pairs there was at least 1 man outliving the paired female at all point in time, and this tend to vary between 1 and 2 men out of 4 over time. And then if we look at the World Population Prospect, database. So we have similar range, so it never goes below 25% either across the world since the 1950 across 199 population. But we see we have a bit more population going above 50%, and this was mainly country from Central and South Asia. Especially, I think here the highest point in that year was Ireland, and also India has been quite high, and Bhutan. But we see that in general across the world, the probability that male outlive female has been somewhat decreasing over time, except for Europe and North America and Oceania that has been increasing, and this is consistent with the HMD data. So population from Europe and North America are generally more presented into the HMD data here. So this was the trend over time. So if we look the trend across the world, so in 2015, 2020, for example, so we see that the Phi statistic was especially high in South Asia and also in West and Central Africa. So if you look at the case of India, for example, it's not because the Phi statistics is low that we have more equality between men and women. So this tend to happen because in India, there was very high infant mortality for female, even higher than for male in the 50s and 60s, even today in certain region. But female has an advantage still above age 15. So there was more equality over the full lifespan, but it doesn't mean that they have equal, sorry, there was more equal Phi if you look at the full lifespan, but doesn't mean that there was more equality between female and male in terms of mortality across the full lifespan either. But then if we look at the other end of the spectrum, so who had the highest Phi, so that's mostly Eastern European countries and of course Northeast Asia generally. So we also look into this correlation between the Phi statistics, the probability of male to outlive female, with difference in life expectancy and standard deviation for both female and male. Here I'm only showing the result for the standard deviation for female. So generally, the smaller the difference in life expectancy between sex, the higher the probability of male outliving female, which makes sense. So there's this negative correlation. Those results are for the HMD country, but we find the same correlation also for the world population prospect. However, we have this positive correlation between lifespan variation, here measured by the standard deviation, and the Phi statistics. So basically, the larger the standard deviation, the higher the Phi statistics. So that means that we know that in recent years, there was a huge decrease in lifespan variation. So that's generally interpreted as a decrease in lifespan inequalities. I mean that people tend to die more and more around similar ages over time. But this also makes it somewhat less likely for male to outlive female. So a way to see to interpret this is that we know that lifespan variation has been decreasing because a reduction in mortality at younger ages. So female basically have a reduction in the right tail of the age at that distribution. So the number of easy outlive female, or the female that are more easy to outlive, has been decreasing over time because they die less and less at younger ages. So in order to outlive female to the same level, male have more and more to shift the age at that distribution towards older ages. So they more and more have to increase their mean. So here in red, for example, this is an example for France. So France had the same outsurvival statistics in 1962 and 2018. So, but we see that the sex difference for the same Phi statistics, the sex difference in 1962 was 7 years, but around 6 years in 2018. So for the same Phi statistics, male had to have 1 year less difference in life expectancy in recent years than in the past. And this is mainly due to the fact that there was way less lifespan variation in recent year. And this relation has been shown, like I said, this outsurvival statistic has been developed in the literature by different authors from different fields. And when you look at the literature on expected failure probability, so they find that if the distribution of both population follow a normal distribution, so with a mean of X bar here and a standard deviation of S, then the probability of failure is the probability of Z, so Z being the Z score. So we see that the smaller the Z score, the higher the probability, as we can know from statistics. So what decreases the Z score is smaller difference in the mean, as we said, the numerator, and large standard deviation. So the larger the standard deviation and the smaller the difference in the mean, the smaller the Z and the higher the probability of failure. So this also proved mathematically, but we know that age-adapted distribution for human does not follow necessarily a normal distribution. So we have other statistical moments that can influence the out-survival statistics, but we still see that the mean and variance still influence the phi, both of them. So as I mentioned, we also look at this out-survival statistics, so the probability of male to outlive female by marital status and by education level. So the first one, the table here, show the result by marital status. So married male have a higher chance to outlive a married female than the unmarried counterpart. So that's vary from 39 to 37% roughly. But if we look at, if you compare married male with unmarried female, basically see that actually married male have a higher chance to outlive female, even above 50%. Similar result also are found across education level. So male with a university degree have a higher chance to outlive female with a university degree compared with male and female with similar education level, but at lower level. But if we look at male with a high university or a high education level, they actually live longer, tend to live longer than female with lower education level. So that also been shown by different studies that first of all, there's greater inequalities between female and male among let's say people that have more detrimental characteristic, if we want, or detrimental social determinant of health, like lower education or lower marital status. So basically what we show here that, and I think that's all, it has been shown also in other studies that the sex difference in mortality is mainly driven by some subpopulation of male that have especially high mortality level. So we have a huge heterogeneity in terms of female and male lifespan, and this kind of out-survival statistic kind of capture a bit this overlap between both distribution and how they can how they're sensitive to this heterogeneity, if we want. So that was the result I have. So just some conclusive remark. So we ask here a bit of a different question that is generally asked when we study sex difference in life expectancy. Generally, difference in between groups are established by looking at summary statistics. For example, difference between female and male or between education group, generally measured by looking at difference into life expectancy or into age standardized mortality rate. So we know that on average, female live longer than male, but we also know that there's a huge variation around this mean that leads to this overlap. So here we study a bit something different, which is just basically how distinct are the two lifespan distribution. So when you look only at the mean, so there's a lot of people, or not academics, but it's often tend to be interpreted as men do not live as long as women, which is on average they don't, but there's still a fair number of men that will live longer than a fair number of female because there's this huge overlap. And this overlap, as I just mentioned, it's the result of the heterogeneity within each population. So not all male have the same education level, the same marital status, have the same behavior, and the same thing for female. So there remain a huge heterogeneity between the two populations that lead to this overlap and that lead to male being able to outlive a fair number of female. And finally, there was this discussion of how this statistics could be informative for public policies. So Jim Vopel came up with a very nice example, so that I can mention to you today, saying like, for example, if people that started working before they were age 20 and retired at 65 and leave on average 5 years less than some people who started working after age 20. So some public policy might be interested into giving more benefit to the people who started, or pension benefit to those who started working earlier in life. But if the outsurvival statistics show that individuals who start working before they were 20 have a 40% chance to outlive somebody that started working later in life, then that means that 40% of individuals will receive higher benefit while still having a fairly high lifespan. So this kind of politics might be more useful if this outsurvival statistic was 10%, for example. So if there was really a huge difference into lifespan, or barely no overlap between people that started working earlier or later in life. There's plenty of possible extension, also future application with the statistics. So we mostly focus our interest, because our interest is mostly into difference in lifespan. But we also can develop some extension of the statistics. So here we look into outsurvival statistic for independent population. So what's the probability that a random female outlive a random male or vice versa? But male and female are generally not independent individual. They tend to be couples. So there's some kind of correlation between female and male lifespan. So after the publication, I came across some statistics where we could account for the correlation or dependence between the population. So that could be a very nice extension. We could also find a way to extend the statistics to account for more than two populations. So far we only been comparing male and female, or people married or unmarried. So they can be more like more pairwise comparison than just one at a time. That could also be an interesting application to cause of death. So what's the probability of dying from cause A rather than cause B, for example? And as I mentioned earlier, so we have this general application, general equivalence of this formula that we can apply to other things than lifespan. So it can be the income distribution, as I mentioned earlier, also age at birth distribution. So what's the probability that a person from a population have a child before somebody from another population, for example. So there's a lot of different application in demography, I think, that could be useful for. Just to conclude, I just want to say thank you to all my co-authors. So Ilya has been I've been collaborating with Ilya on those two papers, Jesus and Virginia on the application paper, and of course Jim Vopel on the model paper. So Jim has been a great inspiration for me, and I think for many of us when it comes to formal demography. And this was my last paper I could do with Jim, so that was very nice to be able to present it to a group that actually like formal demography too. So just a few references that I've been mentioning as well through the presentation. So and if you have any question, I'm really interested to hear them.
Great. Thanks so much. That was just a fabulous presentation and really nice to see both the mathematical formulations and also the applications, and talking about how we, I mean, my main question was like how these compare to differences in life expectancy and lifespan inequality, and you just answered it. So now I have no more questions.
Okay.
But no, it was fabulous. Thank you so much. If people have questions, feel free to raise your hand or put them in the chat, whatever you feel most comfortable with. Does anyone have anything that they would like to ask? Okay. Oh, yeah. Philippe?
Yeah, thank you. Thank you for the presentation, and thank you for the paper. I was wondering if because I have the question when you present the variation by education level, that the tendency is the same for all the levels. I mean, in the university is high, is higher for when males get married with females with less than high school, but also the same tendency for males with lower education and married with females with lower education. This is like a tendency. Maybe do you know why this happened?
So if I understand well your question, you want to know why basically the probability of male to outlive female from high, like that both have a high school diploma, have the same chance to outlive somebody from that the same probability that male outlive female if they both have less than a high school diploma.
Yeah.
That was your question, yeah. So I've been playing a bit more with those data for another project, and it seems that there's not a huge difference in lifespan between individuals in the US that have a high school diploma versus somebody that don't have a high school diploma. There's also huge heterogeneity in here because people that don't have a high school diploma, somebody like can have completed or do the 12 years of school, but they might not have graduated for some reason, so they don't have the diploma. From what I've seen from the statistics, they both seem to have very similar lifespan in the US. So that was maybe not the best categorization I could have. But this is this was one of the standard way to divide.
Okay, thank you.
Yeah.
Thanks.
And how?
Doug?
Yeah.
So this is a really interesting kind of topic. I have one question and one comment. The comment is that you've mentioned heterogeneity within these groups a couple of times, and I think you need to be really careful about that. If you're calculating these quantities from mortality schedules in the Human Mortality Database or in the United Nations Population Prospects, if you're calculating the distributions, there is no heterogeneity in them. The calculation is a calculation of the distribution of lifespan, given that every individual follows exactly the same rates at every age. In a real population, if you were using measured distributions, then the question of how many years of high school different people had would be there, because the individuals would have those different experiences. The question that I had was, is there another source of this kind of calculation in actuarial things? There are joint insurance policies for or annuities for married couples or for family members where they need to figure out who's going to die first. What are the probabilities that both members of a couple live for a certain amount of time? I don't know that literature very well, but it would seem like they might have some interesting analyses of that kind.
Yes, so thank you for the comments. I'll be careful about saying maybe variation instead of heterogeneity. And so I don't know, especially in the actuarial literature per se, but I did find some demographic literature about the probability of a wife to outlive his husband or vice versa. So that has been done, and it accounts for the age difference as well between the partners, because female tend to be younger as well than the male in most cases. I think Josephine Goldstein have been doing some research on this, if you're interested. And we did compare what we found with their statistics, and it's somewhat to a similar level. I think it's around 30. The probability that her husband outlive his wife, it's around 35 to 40%, depending on the studies we could find. But I'm not sure actually in the actuarial science what they do. I think it's Tom next.
Yes, this was very interesting, and I thought it was a very good presentation. I'm thinking of generalizations of this, and one of them is, as was just mentioned, to couples where you have different age distributions, different survival functions. You have condition of having reached a certain age. So it's not defined at birth, it's defined at a later age. And I'm sure that this is done by actuaries for insurance and annuities, but they may be doing it in a more computational way rather than working from the more analytical strategy. I'm not sure about that, but I'm sure that the same sort of thing is done. But then going back to the original model that you had, a way to generalize that would be to get at the age distribution of the difference in age at death, the distribution of age at death. So what you're looking at is whether basically whether that difference is positive or negative, depending on how you subtract the two ages at death. But you could say that there is a distribution which is very wide, but very thin out at the tails. And that would be an interesting next step for this kind of work. Thank you
for the thank you for the suggestion. And that make me think that actually we did discuss with some people from actuarial science that they used to study something similar. They used the cupolas actually to look into those questions mainly. So that could be also another application for actuarial science. And thank you for your suggestion. Then Monica said Diego.
Yes, hi, thank you for the presentation. So I have a comment or a question related to, so you outlined some potential areas for future studies or for future applications. And like one thing that came to mind is adding like a kinship component to this. If you could ask, because you mentioned spouses, for example, like probability of outliving spouses, but you could, so like an obvious one would be like probability that like a parent outlives a child or a child outlives a parent, but also maybe between like siblings and this sort of thing. I think that could also be an interesting way to explore.
Yes, I think I agree. That would be very nice. And yeah, I think for this, we have to solve this independence question first. So because it's not independent population. So so I think there's some solution that I haven't been working out the magic yet, but I think it would definitely be possible in what is available in the literature. And I know there's already some statistic available into probability of wife to outlive, or the probability of a husband to outlive their wives. I think that could be extended to a kinship as well. Thank you. And then Vanessa.
So much for just brilliant, breathtaking. I really enjoyed this work. I just got my mind. I mean, just so many things, so many applications, and just really, really happy for this. So when you're talking about this actuarial application, it's more of a comment than a question, is that they use these contingent functions. So you have like, of course, they follow this Demography's law, but you have the mortality of either life. So you can have like, so they can relax a little bit the independence assumption as well. And then you have this joint life status, and then you have the first death and then the last survivor. And usually they use this function, which is similar to what we do as a remaining life expectancy, because it's time until the failure of the first one. The probability the first one goes and the last one goes, which is also very similar to reliability theory, which also Jim was super excited about. Like you have the system where one component fails first and then the other fails, and how much does that contribute to the whole system to fail? So I really think this could be something interesting to connect, because it's the same idea that we have, because what you're doing, I mean, the huge relevance is that somehow you also connect this individual level to the population level through one statistic, right? It's reflecting somehow this over there. And this reliability theory also does this. And you can, I think that if you connect the joint life status that actuaries do, you could do this. And maybe in the future for incorporating heterogeneity, you could use the shared frailty, because they also have this shared frailty thing. So it could be also something that maybe you could incorporate for health. For example, an unhealthy, like you have two, we talk about healthy and unhealthy, but the relationship between health and mortality is complex, right? And we know that sometimes there could be a situation where an unhealthy person outlives a healthy person, right? So I think it would be really interesting to go into that direction. But thanks.
I agree.
Super
Thank
inspiring.
you. Yeah, like everybody came with their own version. That's interesting, and how to improve. So that's a good group. Is there? I don't see any more raised hand, but
Yeah, does
I'll
anyone
share something. Yeah.
Sure. Oh yeah, Hal shared
Yeah.
a poem, which is
Okay.
very, very apt and wonderful.
Okay.
I'll ask a question if no one else has anything at the moment. Well, so first, the practical question: is the code that you use to calculate these things on discrete data available for those of us who are interested in playing?
Oh, it's supposed to. We have. I think we have to update it a little bit, but Ilya created a GitHub because for that, but I don't know how available we made it, but I can look into it and make it very soon available, hopefully.
Yeah, I might follow up, and then if it's okay, we'll share.
Please do. That would force me to actually update it.
Yeah.
Yes.
I know that feeling. And then I guess more of a comment. I find this out survival statistic interesting, because I feel like when we think about prediction metrics in demography, we're very used to like calibration, right? So how well can we predict age at death, or how well, what's the probability of surviving to age 80 or whatever? Whereas this measure is more of a discriminative measure. So it's sort of in the idea of machine learning, you have these, and you mentioned area under the curve. It's very related to this, like if we have a pair of observations, which one is more likely to sort of survive longer? And thinking about, so, you probably know this, but on a lot of surveys, people are often asked, like, they're after this sort of like subjective idea of survival, right? So what do you think the chances that you'll live to 75 are, right? So we have this information on a lot of big surveys. I was working with a group over summer at Max Planck, and we were looking at the health and retirement survey and looking at how well do people predict their own survival, and the answer is not very well, and it varies by demographic characteristics. I'm curious to get your thoughts on, like, if someone was asked, instead of like, what's the chance that you'll be alive at age 75, for example, if someone was asked, think of this type of person, think of someone who has an education of this, what do you think the chances of you being alive longer than them are? I mean, that's a clunky question, but do you reckon people would do a better job at like guessing the discriminative, like the pairwise comparison compared to calibration?
Well, it's hard to say, because I would be assuming also that people know what is the lifespan or the average lifespan of people with specific characteristic.
Yeah.
And so unless you give them a table with, I think this is done sometime when you try to have an expert opinion about future lifespan. You give them that rate from cardiovascular disease has been decreasing by 12%, this by 10%. So what do you think it will be the next 5-10 years? So maybe if you give them a bit of information, but I don't know, because I think people are generally bad at estimating how long they live, but it's a very hard question to give your own lifespan.
Yeah.
So
yeah, I just wondered if they would be better at thinking, oh yeah, I'm going to live longer than that person. Yeah, totally.
I'm living longer than that. So what's I think it's not my expertise, so I don't have.
Yeah, no, I wasn't.
I'm not 100% sure if that would. That's a valid question. Maybe we can look into, but I don't have any answer for you at the moment, sadly.
no,
I
no
don't
worries.
know it. Yeah.
Yeah. Hal, you have another question?
Yeah, this is since nobody seemed to be having more questions. As I understand it, the distributions whose overlap sort of is the basis for these calculations are probability distributions.
Yeah.
Can you use this if they were not? That is, they don't sum to one. They're not probability distributions. They're just two functions. Have you ever looked at that, and does it just turn out to be as simple as a kind of some rescaling factors appearing in the formulas to basically rescale the distributions to integrate to one?
I haven't tried it. So all the formulas are based on distribution, yes. So this is based on so I never thought of it as not distribution. Of course, we're not, I'm guessing like the benchmark. So now we know that, if the probability is lower than 0.5, then there's an advantage for one population compared to another. In our case, like if probability is lower than 0.5, there's a disadvantage for male compared to female. But if suddenly that doesn't sum to 1, I don't know if like we have a distribution that sum to 2. Will be the midpoint 1. I'm not sure if that was your question. I never really play with it, so I just always think in terms of distribution. But that's a good question if everything is a matter of rescaling. So if you have a distribution or some kind of sample that's summed to 100 or 10,000, would the statistics follow the same scale? We never tried, so I don't know, but I would somewhat assume. Yeah.
The example that I'm interested in is when you have a function which is the abundance of a generation of individuals over time. So it starts off at 0, it increases and then decreases, and a subsequent generation that does the same thing, and they overlap, but they're not probability distributions. They don't necessarily have the same area. The generations aren't of the same size, but there's it's interesting to try to think about the way in which they overlap, which is essentially what this is exploring for the context of the survival distributions.
Yeah. So that's an interesting question. I would think that you could use something similar to estimate this, but the level you would compare it with, or what information you could get out of it, or how you would interpret it, I'm not sure. There's different also if you're interested in the overlap, there's different index looking at overlapping between two distribution. That you can look this stratification index by Shi and al. That will give you a percentage of overlapping between your two distribution. Might be more very relevant for what you're interested in. So I'm trying to think fast on how that would work and give you a math, but I'm always a bit skeptical in giving like a fixed answer to like when I haven't actually tried and find the proper answer. But if you want, I can.
That's quite okay. It's just I just wanted to know if you had already solved the problem. Otherwise, it's an as yet unsolved problem, which is what formal demography is good for.
Great. So though it's an unsolved problem, I think it's an interesting problem. But yeah, I think it could definitely be done somehow, but I don't know, and I don't have the right answer for you right now. But if you're interested, we can look into it, and that would be very interesting, I think. In share, Vanessa, you have a comment?
And I was just adding in the chat because Monica mentioned this with the perception in terms of life expectancy, and then they had this vignette surveys, which was aimed at that, but related to health. So for instance, people are very self-conscious about when you ask questions about their own health. So they did this in the survey where they had like an avatar of you. So considering a person like a regular Joe who is this age and has these characteristics, would you consider him healthy or not, and things like that. And it's interesting to see how much we're really bad at assessing our own health. And somehow, like, people who are healthier really tend to, on average, underestimate how healthy they are. So it seems that you're more health conscious. And then you even, so even Sonia Spitzer, a colleague here from Vienna, was also doing this work where this, like, cost-wise, because she's a health economist, she was saying it's interesting how inefficient we're being, because healthier people go more to the doctor and unhealthier people just really overestimate their health. So you kind of have, like, you know, a mismatch. And so it's usually interesting, this negative relationship. So healthier people on average think they are less healthy than they are, and unhealthier people think they're healthier than they are on average. So it's just interesting. I was just a comment where for us it's a health survey, but it's just curious to see.
Yeah.
Maybe we can accommodate 1 or 2 quick comments if you have. So it seems no. Okay.
Seems like everyone's done.
Yeah. So thank you so much, Marie-Pier.
My pleasure.
And Monica and Vanessa, if you want to say something.
Yeah, no, just
For the
thanks for
group.
everyone to showing up, and this was such a fabulous presentation. Thank you so much for sharing this work. This was recorded, and we'll be posting a recording as we usually do on our website. Might follow up with some coding resources if that's okay, so we can share those as well. But other than that, hope to see you in a couple of weeks to hear about the world mortality data set. Thanks everyone.
Thanks everyone. Thanks, Marie-Pier.
Thank you.
Bye.
Bye. Thank you
Bye.
so much.